Typically, all chemical processes are designed to convert raw materials to produce a product that meets all the quality specifications and is ready for the market. These chemical processes broadly involve three steps. Initially, the raw materials are subjected to a sequence of physical treatments to refine them into a form suitable for chemical reaction. This may include the removal of impurities that could adversely affect the catalyst within the reactor. These materials, once treated, are introduced into the reactor, which is the central component of the process. In this stage, the raw materials are chemically transformed, yielding a mixture of desired products along with byproducts. The reaction step typically does not yield pure products due to unreacted raw materials and the formation of byproducts. Consequently, a separation step is essential after the reaction to isolate the desired products from the undesired ones. Materials that do not react are returned to the beginning of the chemical process. This recycling is critical for efficient raw material utilization, ensuring the process remains economically viable. The economic success of any chemical process is critically dependent on the design of the reactor. It requires a delicate balance, minimizing the cost associated with the reactor itself while also accounting for the expense involved in the treating of materials after the reaction has taken place. Therefore, understanding how chemical reactors work lies at the heart of almost every chemical processing operation. In unit operations, we focused on the design of equipment for the physical treatment steps, whereas chemical reaction engineering is concerned with the chemical treatment step of the process. Chemical reaction engineering, or CRE, is dedicated to understanding the rate at which chemical reactions occur and the underlying mechanisms. CRE is also about the design of the reactors themselves, where these reactions take place. The real challenge in CRE is to bring together knowledge from thermodynamics, chemical kinetics, fluid dynamics, heat and mass transfer, and even economics. Our aim is to create reactors that are not just efficient at processing materials, but also cost effective. This balance is key to the economic feasibility of the entire chemical process. So CRE is about synthesis. It's about combining all these complex factors to design a reactor that we fully understand and that operates optimally. And it is this specific knowledge in chemical kinetics and reactor design that really sets chemical engineers apart from the other engineers. It's our domain where we apply our specialized skills to make a significant impact in the field of chemical processing. Now let's look at some examples of industrial reactors. Batch reactors are used in the pharmaceutical industry and in specialty chemical manufacturing. They are versatile and are used for operations where flexibility in operations is required. Tubular reactors are typically used for continuous processing in chemical manufacturing. Its design allows for efficient heat and mass transfer, making it ideal for large-scale production. Stirred reactors are commonly used in industrial applications for processes that require uniform mixing. Its design allows for consistent distribution of reactants and efficient reaction management. This slide shows a catalytic cracking reactor, a key component in the petroleum refineries. These reactors break down large hydrocarbon molecules into smaller, more valuable ones like gasoline and diesel. They are crucial for maximizing the yield of high-demand fuels from crude oil. This is an image of a calcination kiln, an industrial reactor used to process raw materials at high temperatures. This type of kiln is integral to production of cement, lime, and various other materials that requires high temperature treatment to alter their physical or chemical properties before further processing. Microreactors are small-scale continuous flow reactors that allow precise control of reaction conditions. They are used for rapid testing of chemical reactions and process optimization, and are becoming increasingly important in pharmaceuticals, fine chemicals, and research and development due to their efficiency and scalability. Industrial electrolyzers are specialized reactors used for electrochemical processes such as hydrogen production via electrolysis. Raceway ponds are open-air shallow ponds used in the cultivation of algae and other aquatic organisms. They are often used in the biodiesel industry for growing algae that can be converted into biodiesel. These systems allow for controlled conditions to optimize the growth rate of the algae and are an example of bioreactors in industrial biotechnology. To evaluate a reactor's performance, we need to establish a performance equation. This mathematical relationship correlates the inputs like concentrations, flow rates, and temperatures to outputs including product concentration, temperature, and conversion. This equation is crucial for comparing different reactor designs and operational conditions, optimizing performance and scaling up from laboratory to industrial scale. Understanding the contacting patterns is also essential. This refers to the manner in which materials move and interact within the reactor, including the timing of their mixing and their physical characteristics such as clumpiness or dispersal. For instance, some materials naturally form clumps like solids or may not easily mix like certain non-coalescing liquids. Kinetics, the study of reaction rates, is a fundamental aspect of reaction engineering. If reactions occur quickly, equilibrium conditions will largely dictate reactor's output. For slower reactions, the reaction rate alongside heat and mass transfer rates become significant factors in determining the reactor's performance. These principles allow chemical engineers to design reactors that meet specific process requirements. Designing a chemical reactor focuses on maximizing space-time yield. This involves creating a reactor that can produce the highest amount of desired product per unit time and per unit volume while ensuring safety. Several factors influence this. On the reaction side, stoichiometry, the quantitative relationship between reactants and products in a chemical reaction. Kinetics, how fast chemical transformations occur. The distinction between elementary and non-elementary reactions is important because it affects how rates are modeled and predicted. Elementary reactions have a rate that is directly proportional to the concentration of reactants, while non-elementary reactions have more complex rate expressions. Single versus multiple reactions. Whether one or multiple reactions occur simultaneously can impact the yield of desired products and the design of the reactor. On the reactor side, isothermal versus non-isothermal operations. An isothermal reactor maintains a constant temperature which can simplify design and control, whereas non-isothermal reactors have temperature variations that can affect reaction rates and yields. Ideal versus non-ideal. Ideal reactors, such as a perfectly mixed batch reactor or a plug flow reactor, greatly simplify the design equations. However, real reactors often exhibit non-ideal behavior due to factors like incomplete mixing or channeling. Steady state versus non-steady state. Steady state reactors operate at constant conditions over time, which can be easier to control and model, while non-steady state reactors have conditions that change over time, such as batch reactors. Chemical reaction engineering encompasses these topics, providing chemical engineers with the tools to approach reactor design problems with confidence and efficiency.